Okay, sorry I was late. I had to reboot the system in the room next door. Next door, can you hear me? All right, thank you. I just saw the weirdest thing walking over here. Like, you know how you walk past the library and you've got the bottom bit where you can all study and stuff, right? And all the windows, you can see inside. There's a dude there eating a red capsicum, like an apple. Like, I stopped and looked. Like, I thought, surely that's not what I think it is. He's reading. Who the hell eats raw red capsicum? I mean, I love capsicum, but I don't eat it like that. I sat there for a good 30 seconds thinking, what are you doing? Weird. Anyway. Very weird. Well, is there something about capsicums I don't know? That's strange. Anyway. First things first, a student pointed out there was a typo in the lecture notes for this week, so I have re-uploaded them this morning. If that person's here, thank you very much. I had this, the best linear approximation for a function, I had it written as f dash of x times x, and it should be f dash at a times x minus a. So I have fixed that and re-uploaded. You can either print it out or just write it out on your thing. Second thing is a couple of people already started on the so-and-so assessment that's due this Sunday, and there's an issue with one of the questions marking you wrong for the maxima and minima, right? Has everyone experienced, some people experienced this already, where it's a drop-down menu and you're supposed to select local max, local min or saddle point, and it's marking you wrong no matter what you put. I think I fixed it, but you know, if it keeps stuffing up, I will fix it manually at the end, but I'm pretty sure I have fixed it now. I couldn't actually find out what the problem was, so I just copied the question from another one. So if you've already done it and it's marked you right, it's fine. But to see the new question, you'll have to stop the test and restart the assignment and restart the whole assignment. But it should be fixed now. As I said in the first day, I'm going to be very lenient with the so-and-so stuff. I mean, I'm not a fan of these things because of stuff-ups like this and syntax errors and things like that. So, but it should be fixed now, okay? All right. What we did in the first lecture was look at Taylor polynomials for functions of a single variable and looked at the remainder term. Now, for a function of a single variable, basically we can find, when I ask you a question on this, you can find the Taylor polynomial to any order you want. I'm not going to be stupid about it. I'm not going to ask you to calculate 1 to order 27 and expect you to find the first 27 derivatives of something. I'm not going to be that silly about it. But in theory, it keeps working, right? You can go up to any order n. There is equivalent of a Taylor polynomial, idea of Taylor polynomials for functions of several variables as well. But for those ones, we'll only go up to the quadratic term. Now, the reason for that is to calculate higher terms, because you remember the problem with functions of two variables is the sheer volume of derivatives we get. There's 2 first orders, 4 second orders, but of course 2 of them are equal. There are 8 third orders, but 3 of them will be so on and so on. So it gets rather tedious. The easiest way to calculate all the terms up to order n for Taylor polynomial functions of several variables is use the ideas from tensor calculus, tensors, which you don't do in first year. So basically, you remember you got a vector. Remember, a matrix is like a vector is a special case of a matrix. Right? So you imagine a vector is like a row vector. Matrix, you add another dimension, so it becomes a cube of numbers, say, a square of numbers. Tensors keep going. So a second order tensor is a 3D thing of numbers. But then there are higher, which you can't visualise anymore. And to calculate the higher terms is easy as with tensors, but we don't do tensors in first year because they're awful. And you need a lot of experience with matrices first before you can hit tensors. So we'll just stick to the second order one for functions of two variables, and I'll just state the formula. It is proved up to this order in the unit reader if you're interested, using the idea of a Taylor series for a function of a single variable. So it's in the unit reader, but just like the tangent plane is a logical extension of the equation of a tangent line, this one is a logical extension of Taylor's polynomials for functions of two variables. So the formula is basically this one, and we're going to stop at this order. There is a remainder term as well, but it's very awful to use. We're not going to do it, right? I only worry about errors and stuff for functions of a single variable. Right, but you can sort of see that the first two terms are exactly the equation of a tangent plane, and then there's a correction which will bring in some curvature, if you want, and that's where we'll stop. Right? And you see that the second term is basically all of the second derivatives, but of course since the mixed ones are equal, hence the 2 times, I mean technically it's fxx times x minus a all squared plus fxy times x minus a times y minus b plus fyx times y minus b times x minus a. They're the same term, right, because the mixed derivatives are equal, plus the last one involving y, right? So this one's very much a matter of calculate all the derivatives, evaluate them at the point I'm asking you to expand about, plug it in and simplify, right? And this is on the formula sheet as well, so you don't have to remember it. And it's proved in the unit, there's a proof of this in the unit reader if you, so as a simple example, you see it's very much a process of just calculating and plugging it in, right? So let's say we've got this function, this surface, the square root of 1 plus x squared plus y squared, and I want the first order Taylor polynomial and the second order Taylor polynomial of this approximation of this thing about the point 0, 0. So the first order approximation is basically just the equation of a tangent line, tangent plane, I should say. So if I find the partial derivatives, the problem here is that that's a fairly useless approximation because it's just the plane z equals 1. But if you want to go the next order, you calculate the second order derivatives, and you evaluate them, and you just basically plug it into the formula. So an approximation for this surface is 1 plus a half times x squared plus y squared. And it's the same idea, where you're turning nasty things into things involving just powers of x and y. Right? And here I've got, the red is the actual surface itself. The blue is basically an approximating it near 0, 0 by a tangent plane, which you can see is fairly useless. Right, but the second order one brings in some curvature, and it's like the idea, you can imagine you go out a bit, higher orders you go, you can go out a little bit further, okay? Right, but we'll stop at second order, right? But very much the process, there's no error, we're not going to cover the error term or the remainder term for this one, right? So it's basically just a matter of doing it. Just, you know, it's one of those simple things where you just do all the calculations, they give you the formula on the formula, you just plug everything in. So for example, I've got this surface e to the 2x times cos of 3y, and I want the second order Taylor polynomial of this function of two variables about the point 0, 0. So I do it in a very similar way to functions of a single variable. I work out all the derivatives I need, so we're only going to go up to second order, so I just need all the first and second order partial derivatives. And as always, I always do that habit where I calculate this. Although I haven't explicitly said, I do this both ways. It's like a self-check, right? So if I differentiate this with respect to y, or this with respect to x, remember, I must get the same answer, otherwise I've stuffed something up, right? Then I just calculate everything at the point I'm expanding about, and just plug it in the formula and clean it up. That's all I'm looking for, okay? So very much just chuck it in and do it, yeah? Okay. Right, so do have a work through that example. It's very similar process function of a single variable, just more derivatives to find. And unlike the single variable case, there's going to be no derivatives and things like that. Okay. All right, as I said, in Math 101-2, you'll start learning about infinite series and infinite sequences, or mainly infinite series. And then you'll learn about Taylor series instead of Taylor polynomials and how useful they are. And as I said, one of the main things we use them for is to calculate integrals that we can't normally calculate. Right? So integration is what we're going to spend the next couple of weeks on. Right? So that's what we're going to do next. Right, let's go through some revision first. Right? Everyone should know all of this. Right, but let's just do it, right? So the definition of an integral was basically motivated by this problem, right? So the motivation for the derivative was actually motivated by find the rate of change, right? And whereas integration initially seems like a totally different, you wouldn't think they were linked initially, because integration is asking a completely different question. Basically, the idea behind what motivated the concept of integration was, given a curve y equals f of x, how can I calculate the exact area bound by that curve in the x-axis? And that's what the integral is. So it actually took a while for mathematicians to discover the link between differentiation and integration, right? That they're opposites of each other, because it doesn't, one's differentiation's rate of change, integration's area. How the hell are they linked? Well, it turns out they are by the fundamental theorem of calculus. Right, so the definition is motivated by the, calculate this shaded area here, and this is what I define the definite integral to be. So a definite integral is an integral that's got limits, right? So some terminology and some notations. If the function lies above the x-axis, we say that the area is positive. So notice I use area in inverted commas, right? Because if a function drops below the x-axis, its area and definite integral are not necessarily equal, because if the area is below, it's a negative area and things cancel, right? So if the area is above the x-axis, we define the area, the definite integral to be positive. If the function's below, we define it to be negative. It's like a negative area. Just like the height above the x-axis, and we use the term height loosely. When we plot a function, it's the height above or below. And if it's below, the height's negative. Same idea. The area is also defined to be positive in the direction of increasing x. So what I mean by there is, if I take the definite integral from a to b, that's in the positive direction. But I can also ask, what is the integral from b to a? I can go backwards, and then the area will be negative, right? So it's positive above above the y-axis, and positive in the positive x direction, negative otherwise, right? And this is just to make it well behaved. So then the area is written as the definite integral of the function f from a to b, and this is how we write it, right, with the integral sign and the limits. So this is called a definite integral. Ones without limits are called indefinite integrals, right? So this is a definite integral. This symbol is called the integral sign. The reason why it has that funny looking S shape will become apparent when we look at the formal definition of integrals in a few weeks. The function we're integrating is called the integrand, and a and b are called the limits. A is the lower limit, b is the upper limit. So in words is written the integral of f from a to b with respect to x. So that's what all this means. The integral of this function from a to b with respect to x. That's basically how we say it in words. Right, some properties. The first one's basically the same, that if I go in the opposite direction along the x-axis, all I do is change the sign. So the integral from a to b is minus the integral from b to a if I go backwards. By definition, we say if the upper and lower limits are the same, the integral is defined to be 0. This is to make it nice and continuous and well behaved, right? So, and then we can link it to differentiation. Just like derivatives, constants come along for the ride. When I'm doing integrals, I often take the constants, although when I do derivatives, I just bring the constants along. When I do integrals, I often group all the constants outside so I can concentrate on the integral itself, right? Because that's the hard bit, right? So constants just come along for the ride. The sum or the difference of two functions, I can attack each one separately, just like we do with differentiation. And the last one is basically saying I can split definite integrals up into sums of different areas. We probably won't use this property that much in this unit, but when you do Math 101-2, you'll study a special type of integral called an improper integral. And sometimes you'll have to do this to handle them properly. It's quite a simple idea in theory. If you've got some value c between a and b, so look at this picture on the right. Basically what it's saying is the left area plus the right area equals the total area. Duh. Right? That's basically what it's saying. Then they've got the fundamental theorem of calculus, because it's called this obviously because it links differentiation and integration. If a function is continuous on the closed interval between x equals a and x equals b, and if capital F is an antiderivative. So in other words, the derivative of capital F is little f. The derivative of capital F is the integral of the function you're trying to integrate. Then the fundamental theorem of calculus says that the definite integral from a to b of little f equals its antiderivative evaluated at the upper limit minus its antiderivative evaluated at the lower limit. Right? Again, we should all know this. And this is how it's all linked. Believe it or not, this took a while to figure out. Right? So people used to do integration and differentiation as separate topics. I mean, back in the day, you could only do integration approximately. Right? And I'll show you how we do that when we do Riemann sums in a few weeks. Right? But then this was, I don't know who the hell, I should know who discovered it, but I have no frickin' idea. And they're linked, right? Which does seem odd because they're doing totally different things, but they are linked. This also shows the other problem. As I've said, differentiation can always be accomplished, always. Right? No matter how complicated the function, you can always differentiate. There's no such thing, there's nothing you can't differentiate unless the function's really weird, like not continuous or something like that. But integration can't always be done. That's what makes integration so difficult. Right? And I'll show you, well, basically what we're going to do is a bunch of strategies on how to do them. Now, there is different notations for all of this. I mean, as always, unless you've invented the notation yourself, I'm aware of it. All right, so if you're doing a definite integral, so let's say I've got the integral from a to b of, let's make it easy, x dx. Everyone, well, let's actually put some numbers in. Let's make it integral from 1 to 2. All right? Different ways you can do it, right? Depending on the notation. The way I've learned to do it is I use square brackets and I integrate x, so that's just a half x squared. So this is the notation I use, right? Applying the fundamental theorem of calculus. And what it's basically saying is take what's in the square brackets evaluated at 2 minus what's in the square brackets evaluated at the lower limit, right? And then you just do it. Other notations, some people use curve brackets. That's fine, I don't give a crap. Some people just use the big, like evaluated at thingy, vertical, I don't know what the hell you call it, big vertical line thing, whatever, right? That's fine. Right? And yeah, there's a couple of others. They're probably the three main. I don't care. You know, I'm assuming you've all done integration. You're all well familiar with the basics of integration. If you're, as I said, unless you've invented the notation yourself or it's really weird, I'm familiar with it. You don't have to use my notation, right? But I do the square bracket. I do it the square bracket way. Okay. But if you're unsure, show it to me, right? And I'll tell you if it's okay or not. It probably is. So. Okay, all right. All right, and this is how we handle definite integrals. What we're going to be concerned with is actually not calculating the integral, but actually finding an antiderivative. That is by far the hardest part, right? Because it can't, sorry? Somebody say, no? Hearing things, right? Because that's the hardest part. So when we have an integral without limits, this is what we call an indefinite. So in other words, an indefinite integral is, don't calculate an area or anything, find me a function that's the antiderivative of what I've asked you to integrate. Right? So the way we write definite integrals, it's the same thing, which just doesn't have limits. Right? So the important thing is a definite integral is a number. Technically, it's an area. But it could be positive or negative depending if the function sits above the x-axis or below the x-axis, or if we march in the positive x direction or the negative x direction. Without limits, all I'm looking for is find me a function capital F whose derivative equals little f. And we always write indefinite integrals as with a plus c, which we call our arbitrary integration constant. I use a capital C, some people use lowercase, I don't care, as long as it's there I'm frickin' happy, right? But you will lose marks if the C is not included. This is not us being stupidly pedantic. There is a reason for the plus c. It's very important. In my opinion, those of you who are studying engineering and physics or looking to become applied mathematicians, the most important thing you'll learn is how we solve differential equations. Differential equations are basically what we use to model the real world. You've already done it without realising. Who's done physics? I assume almost everyone. Everyone's done, force equals mass times acceleration. Yeah, acceleration is the first derivative of velocity or the second derivative of position. So if you want the position of something, you have to solve f equals m times d squared x on dt squared or something like that, don't you? And you've got to integrate it twice and off you go. That is a differential equation, albeit a very simple one, but it is a differential equation. And the integration constants are how you find the particular solution you want compared to depending on the physical problem you're solving. So the plus c is crucial, and you will lose marks if you forget it. Right? And there is a reason. We're going to do differential equations in the last week or two, and we'll start seeing where it comes in there. Right? Now, just like with differentiation, I give you on the formula sheet. So remember, the last page of the formula sheet is probably the one we're going to use the most. Right? And I give you a bunch of integration forms. So the way we've been using this so far is the central column is the function and its left-hand side is the derivative. The right-hand side are their indefinite integrals. Right? So you'll notice that the derivative of x to the n formula works no matter what n is. Right? I've been saying that all along. But the integral formula for x to the n doesn't work when n equals -1. That's why it's separate in this thing. So we should all know that the integral of x to the n is x to the n plus 1 on n plus 1 plus c for all n except -1. And of course the reason for that is twofold. Obviously that bit blows up when n equals -1, right? And of course the integral was never infinity, right? And of course the other obvious reason is we know that the derivative of log of x is 1 on x. That means that the integral of 1 on x is log of x plus c. Yeah? That's why that one's separate. Right? Notice I've added plus c to every single one of them to ram it home that you must include the plus c. Right? I'm being kind there. Give me a clap. Yes. Right? It's to remind you, add the plus c. Right? And again, it's not us being annoyingly pedantic. There is a reason, a very important reason. All right, now most of them some of them you should already be familiar with, or they're logical, right? So, the integral of x to the n and the integral of 1 on x and e to the x, I expect you know those already, right? So the integral of e to the x is easy, because the derivative of e to the x is e to the x, so its integral is e to the x as well, right? And the integrals of sine and cos, I expect you're already familiar with those. The integral of sine is minus cos because the derivative of cos is minus sine. And we can bring constants and do whatever the hell we want with them. And the same, the integral of cos is sine because the derivative of sine is cos. Right? But then a couple of other ones there you probably haven't seen before. So the integral of log of x is x log x minus x plus c. That's using a technique called integration by parts, which we'll cover next week. Right, so I can't prove that to you yet. What you could, though, is as a fun exercise, if you differentiate all the functions in the right-hand column, you get the central column. Right? The integral of tan and the integral of cot are done by integration by what I call basic substitution, which I expect you already know about. We're going to review it in a sec anyway. The integrals of cosec and sec are done using something called a half-angle substitution. Very weird one, that one. I show it to you basically to prove those two formulas, but it's a weird one. We're going to do that next week. So we'll prove those next week. And then the last three, the integrals of inverse sine, inverse cos, and inverse tan, they're proved using integration by parts. Right, so we can't prove all of these yet. The second thing I want to illustrate is that with integration, this table actually has a lot of information. Just as this column is the integral of this column, So therefore this column is the integral of this column. Right? So if I ask you what is the integral of 1 over 1 plus x squared, it's inverse tan plus c. Done. Right? So this table actually has a lot, it's got a bit of duplication as well, so it's, you can think of it, well these two entries are saying the integral of 1 on x is log of x, which is exactly what that, right? But you see there's actually a lot more integration formulas in here than you initially realise, right? So as a hint, when you've got integrals involving the trig functions, right, look here first. Right? You might be in luck. So for example, if I ask you what is the integral of, sec squared, tan, because the derivative of tan is sec squared. So there's actually a lot of information on this thing. Okay? And the rest will prove as we go. Okay? And obviously you're always going to have this. We'll take this as given. Okay? Now, here's the fun bit. With differentiation, one, it can always be done, and two, we've only got three rules. The product rule, the quotient rule, the chain rule. There are no more. You might find some more on Google or something. They're all rubbish. They all follow from those three. Those three are it, right? And it's usually pretty obvious which one you need to use, isn't it? You've got a product of functions, product rule. Right? You've got a ratio of quotient rule. It's usually really obvious which one you've got to use. Integration, unfortunately, not so obvious. Right? And so the skill with integration is one that comes with practice, and there's no other way around it. It's just practice, practice, practice. Right? There are many different techniques. There's integration, the three main ones are integration by substitution, integration by partial fraction decomposition, and integration by parts. And integration by substitution involves several subclasses. There's what I call integration by basic substitution. By basic, I don't mean easy. By basic, I mean the substitution is obvious. It's kind of like the chain rule for differentiation. Right? What to substitute will be sometimes, not always, but sometimes be staring at you in the face. Right? But then there's integration by trig substitution, integration by inverse trig substitution, and integration by half angle substitution. They're the main ones, which we're going to do them all. Right? Now the difficulty is choosing the right one, and skill at this only comes with practice, unfortunately. Right? Now, obviously, I've been doing this a lot longer than you. I can look at an integral and know what's the best way to do it. That's the other problem. Integration can sometimes be done two totally different ways. Right? Now, when you use things like, Wolfram Alpha or something online to check when you use some computer algebra system to do integrals for you, computer algebra systems aren't smart. Right? And they will usually use a stupid method. Right, where doing it by hand is the smarter one. So sometimes you might want to check your answer, say, right, and you look, I just plug it in online, find an online integrator, plug it in, you get a different answer, you go, oh crap, what have I done wrong? You're not necessarily wrong, right? Not necessarily. I'll show you this with some examples, right? And the big one is, unlike differentiation, integration can't always be done. And I also cannot give you any hard and fast rules about what to do when. I can give you a hint, occasionally. The only hint that usually works is if there's a square root in the integral, you will do whatever it takes to get rid of it. Right? So you either substitute what's under it, or you use an inverse trig substitution to annihilate it. Right? But anything else, it depends on the question. Right? I'll show you what I mean though when doing some examples. But usually when I give integral questions, I make absolutely certain that I haven't stuffed it up, because it is very easy to stuff this up. Or if you write the question down wrong, you could have one where you work on it for 20 minutes only, you're doing one that's actually impossible, right, and can't be done. So read the question carefully with integration. If you get a sign wrong or a power wrong, you could royally ruin your day. Right? So read the question carefully, and I promise I will do the same when I write the damn question. Right, so that I don't do that. I did make this mistake once, A couple of years ago I was teaching a unit on differential equations, and just before the semester started I got pneumonia. I was extremely ill, so I was literally barely ahead of the class in terms of preparing lectures and stuff like that. And the one time I decide I will release an assignment before I've written the solutions. The one time I do it, I had an integral in there that was awful. All right, so when I was writing the solutions out, of course, the class has already started this assignment. This integral took me about 6 pages of algebra to do. I thought, oh my God, what have I? This is an absolutely shockingly bad integral. And about a third of the class got it. I was very impressed. It was really nasty, but they weren't happy about it. Right? But I'm very careful about this. This is the problem with integration. Read the question carefully. Right? So unless we, as in me, make a mistake, every integral you encounter in this unit can be done somehow. The trick is how, right? And this is a skill that comes with practice, right? And as I was showing you, this funny comic that I was showing yesterday, right? Because this is what integration often feels like, right? Differentiation, easy, right? In theory, easy. Sometimes the algebra might get hairy, but you know how to do it. I hope. Integration, not so much, right? I just love this one. There's this nope, and we're going to do all of these. So partial fractions we're going to do. Riemann integration I will show you the gist of. We're not actually going to do Riemann from first principles because it's stupid. Install Mathematica, that's a computer algebra system, right, that'll do it for you. Phone call to mathematicians, don't call me, but Risch algorithm is a high-level algorithm to try and decide how to attack an integral, not something we're going to see. Bessel function is a special type of thing. But you see, the point is, this is the problem with integration. Right? It can't always be done, and knowing which strategy to choose is a skill that only comes with practice. Okay? Anyway. I thought that was a perfect summation of how annoying integration is. And as I said yesterday, I like these 4 really show it. Right? They all look kind of similar, don't they? Right? The first one, straight off the formula sheet. Second one, that's integration by parts. We haven't done that yet. Third one is a simple substitution, right, which we're about to review. Fourth one, you can't do, right? And but you see, they're all so similar, right? But that fourth one that baffled people for ages. And so the way we handle these ones is, because there's so many integrals we can't do, is we invent functions that do it for us. Right? And as I was explaining, most applied mathematicians will have this book. Right? So you see how thick it is. Right? It's a handbook of mathematical functions. Don't go and buy it. You're not going to need it. Right? Right? But it's basically it's like a massive formula sheet. Right? Because all it's full of are formulas. Right? Now, just show you something interesting. Here's the table of contents, right, of the first page. So the first chapters, I don't know, don't worry about chapters 1 and 2 and 3. Chapter 4, that's logs, exponentials. In the old days, trig functions were called circular functions, and hyperbolic functions, which are like trig functions. Right, that's one chapter. All of the rest, the exponential integral, the gamma function, the error function, the Legendre function, Bessel function, Struve functions, confluent hypergeometric functions, Coulomb wave functions, Jacobian elliptic integral, these are all integrals that we can't do. Right? And so the way we do it is we invent a new function to handle the integral. So for example, if you look at the chapter error function, it's an old book, so it's also got lots of, no one does this crap by hand anymore. But it's an old book, but it's very, very, very handy. Right? So this is the chapter on the error function. Just to show you, this is how look at how the error function is defined. Is the integral of e to the minus x squared. right, is the error function, which we call ERF, right, for error function, right? And almost all the functions in this book are because we've hit integrals we can't frickin' do, right? So that's the problem with the integration. And all of the functions in this book are defined, most of them are defined like this. So I remember when I bought this book because in my PhD thesis I got a differential equation that involves an integral and I needed its solution involved chapter 13. And believe it or not, you can actually probably see that that's where this book opens. Right? Because that's the chapter I use. See, it's split, right? Because this is the chapter because I had to work with this god-awful function, right? But it involves an integral in there somewhere. Where is it? Here, down here. All right? But that's the thing. All I'm trying to illustrate here is this is what makes integration so difficult, okay? All right. And again, I like this one because they look so similar. You know, 1, 2 and 3 we can do, 4 we can't. Right? And even changing it a little bit, like here I have this is a computer algebra system that's, it's like Mathematica. You can't see. It's like Mathematica, but it's Mathematica's competitor. This is the one I'm used to using. It's called Maple. And here, for example, I'm asking it to do some integrals for me. Look at, the integral of e to the x squared, that involves, it's actually the complex complementary error function, is the way I've written it. Look at that one for the integral of e to the x cubed. What the hell is going on there? Right? So that involves complex numbers. You can see that -1 to the 2/3. How the hell do complex numbers come in? They do. Right? And the gamma is a gamma function. That's like the functional equivalent of the factorial function. So that gamma to the 2/3 is like, what is the factorial of 2/3? You think, what? Right, but it does exist. Right? And this one over here, that's called the incomplete gamma function. Oh, awful. Right? And just to show you, if I actually calculate it all, right, it involves complex numbers. Right? Very, very... No. But the point I'm trying to... This is the problem with integration. Okay? Anyway, I'll show you some more of this things with this tomorrow. But let's go back to... Oh, no, don't do that. First one that we'll review, which I assume you've done before, is what I call integration by basic substitution. But by basic, I don't mean easy. Now, I'm going to show you my method. If you use your own, it's fine, right? But I'll show you the way I do it, which I find helps. And I'm going to do it by doing not a standard example, but this example shows a useful result, right, that makes sense. Right? So the challenge, of course, comes from choosing the right substitution, and I can't give you any hints. But once we've done all of the integration strategies, integration by substitution is what you try first. Right? If that doesn't work, you go to the more advanced ones. Right? Or unless it's obvious that it's not going to work. Right? Again, it's a skill that comes with practice. Now, I'm going to illustrate the method by looking at a useful example for a definite integral. Consider this definite integral where a is some constant, so it's a definite integral between minus a and a, and all I've told you is that the function is even. Right? So remember what an even function is. Replace x with minus x, you get the same thing. Things like a quadratic. You know? Right? So an even function is one where you replace x with minus x, you get the same answer. Here's how I do my change of variable. Don't worry too much about on the left. Look at what I'm doing on the right. So when I do them, I write a little heading, change of variable. This is where I work everything out before I attack the integral. And if it's a definite integral, I change the limits now instead of later, because I used to always forget when I was a student. Right? But I bring in, you use the same letters like with the chain rule. Let u equal minus x. I solve that for x in terms of u only if it's easy to do so. and only as a last resort would I use that information. I need du on dx, just like we do with the chain rule, and I need an expression for du involving dx. Right? Once I figure all that out, I attack the integral on the actual integral I'm doing. But the key is note what I've done on the right. Right? And this is how I actually do it. Once you do this one, though, what you'll discover is that if the function is even, the integral between minus a and a is equal to 2 times the integral between 0 and a. Right? And having one of the definite limits 0 is always good. Right? Always saves work. You can also show that if a function is odd, the integral between minus a and a is 0. No matter what f is, as long as it's odd. And this makes sense if you go back to the idea of areas. Right? If it's even, it's symmetric about the y-axis, isn't it? So the area on the left equals the area on the right. So you find one of them and double it. If it's odd, the area on the left is the negative of the area on the right because it's below the x-axis. Or they might be the other way around. Like the left one might be above, but the right one will be below. So when you add them, they cancel and you get 0. Okay? But some important things to note. For definite integrals, you need to change the limits as well. Doing it where writing everything on the left, so write the integral on the left and do all your change your variable on the right is a good habit to get into, especially as the problems get more complicated. Okay? Try to pick a substitution whose derivative is in there somewhere so things cancel. Right? This is what I mean by basic substitution. A lot of the times it will be obvious because the derivative of something is in there. The aim of the game here is to make an integral so the formula sheet helps you. Right? So you can write an integral in such a way that the formula sheet will give you the answer. Right? That's basically the aim of the game. Just like with the chain rule. The chain rule for derivatives, the whole idea is to break it into smaller pieces that the formula sheet tells you how to differentiate. Yeah? This is what integration by substitution is doing. Get an integral that something that you recognise you can do. Okay? All right. And here's some classic ones you're probably already familiar with, although I must admit personally I hate these formulas, right? Just like with the chain rule, if you're ever unsure, do a substitution, right? But again, as I said, I expect that you've seen all of this before. Now I do have some examples. What I would like is to refresh your memory and have a go at these. We're going to do more of them in the last lecture anyway. Right, but have a go at some of these to refresh your memory about, and also take note of how I do it, right? And although it might seem more work, as the problems get more complicated, this will help, okay? But we'll work through these in the lecture on Thursday, all right? All right, so thanks everybody. I'll see you then.